Today we welcome Dr. Tracy Mandel. She's an assistant professor in ocean engineering and mechanical engineering at the university. She joined us in 2020, and what a year she's had. But she comes to us with an expertise in fluid mechanics and environmental engineering. So questions for the virtual seminars are going to be handled. You can type them into the question and answer box that is available if you look at the bottom of your Zoom screen. And then either Alyssa and I will read them to Tracy and she can answer them. If you prefer to read your question aloud, you can utilize the raise hand feature that is also at the bottom of your Zoom panel, and then we'll unmute you and allow you to ask the question. So with that, I'd like to thank Tracy for sharing her work with us today and hand it over to you.
Thank you, and nice to see, well, not necessarily see everyone, but nice to all gather together again. Here we can pretend we're all in Chase. So as Annie mentioned, I'm an assistant professor here at UNH. I started in January. Very excited to be here and excited to be able to come back on campus a little more in the fall. So today I'll be talking to you about secrets from both the deep and the shallow. And my presentation will talk about how we can use experiments in fluid mechanics to study things like oil spills, seagrass meadows, and I'll also talk about some future directions I hope to go in here at UNH. So I'll start with two case studies from some of my prior research. We'll first look at how we can use experiments to answer the question of whether the water surface can give us information about submerged aquatic ecosystems like the seagrass shown here. And then I will transition to talking about some fluid processes that can affect the subsurface retention of oil droplets. And then finally, I'll close with a brief discussion of three projects I'm starting up here at UNH and hopefully get to introduce some of the new students working on those projects. So let's start talking about this first topic. And so this project, which comprised most of my PhD work, was looking at the bathymetry inversion problem, which asks, can the water surface give us information about bed roughness? And more specifically, how do interactions between aquatic ecosystems like seagrass and other submerged vegetation, how do interactions between these ecosystems and the surrounding flow manifest at the water surface? And so before we go, out into the field and start trying to observe the water surface, and trying to pick out where seagrass beds might be, how healthy they are, their spatial extent, we first need to look at the question in a controlled laboratory setting to understand what sort of signature might we even be looking for. And so that the way, I guess, my laboratory setup of choice and most people that look at flow through submerged vegetation in the lab is to use a model seagrass canopy in a flume, basically the water equivalent of a wind tunnel. So here is a video I'll show you guys. It might be at a very low frame rate for you, so I apologize. But this will be showing some dye being released vertically in a lab setup. This was done in conjunction with Haiyun Chung, who's a PhD student at Stanford when I was still there. So you can hopefully see a little bit. The dye is kind of tracing out the profile of velocity over the water column. So we get flow, much slower flow within the canopy, within this model seagrass canopy, and we get much faster flow above it. So prior work has shown that this sort of canopy flow is analogous to the canonical mixing layer in fluid mechanics, where you have a stream of slower moving fluid and a stream of faster moving fluid that meet and mix together. And this can create this train of swirling masses of fluid known as a vortex, or the plural is vortices. So if you hear me talking about vortices, that's what I mean, these swirling fluid masses that you can see in this flow visualization. If you can see my mouse, you can see it right here. And so in a canopy, we have this same sort of mixing layer behavior where vortex structures are generated and then propagate as a train over the canopy surface, or over the canopy. And so this is a signal that we're going to look for in the water surface. So to look at this, I set up an array of 8 cameras looking down on the canopy. You can see I've painted the tips of some of these canopy elements, some of these little wooden dowels white for greater contrast. You can see the camera array that is set up here. So we use this to measure the flow. The analogy here is sort of if you were looking through the water surface at the bottom of a pool that had some pattern, and if there are ripples in the water surface, that fixed pattern at the bottom appears to wobble or be distorted or displaced. And so the sort of data that we get with this setup looks like this. Again, I apologize for probably some choppiness here, but you can see in the upper left panel that this is a raw image from one of our cameras looking down at the tips of these round cylinders. If we zoom in on just one of those tips, recall that this is a rigid wooden dowel, so it is not moving. But we can see that the tip of that dowel appears to kind of wobble in the streamwise direction, which is the up-down direction in these videos. It appears to wobble over time. And so we can use some particle tracking codes to track the apparent displacement of that circular tip. And that's what's shown in the bottom panel. So we see this oscillatory, somewhat periodic motion that's happening. And so prior work has shown that if you're tracking the displacement of fixed features at the bed in shallow enough water, you can relate this to the slope of the water surface. So the slope of our water surface, or more specifically perturbations in the water surface slope, are a function of the displacement field, delta R, that we're measuring in this bottom panel. The ratio of the refractive indices of our two media, so water and air, H minus HC, which is the gap between the water surface and the tips of the canopy, so the, available space for these vortex structures to occupy. Got a figure in the next slide, and then the height of the camera. So we can, we have an array of 8 cameras set up, so we can then take this signal and look at it over the entire canopy length. And so this is a contour plot in the upper panel of perturbations in the water surface slope over a kind of cartoon side view of our canopy. So these are very small perturbations. You can see this is, 4 times 10 to the minus third, but they coincide with these, approximately 2-dimensional vortices or rolling masses of fluid that have a characteristic shedding frequency and a characteristic wavelength and a characteristic speed. So you might have actually seen a signal like this, very similar to this, if you've ever driven by maybe a farmer's field. This does, we see this phenomenon in the real world. So this is caused by wind blowing through, and I apologize again that this may be jerky, but you can see these kind of bands of dark and light where the terrestrial vegetation is bending in line with these vortex structures that are being shed. So this is in the, whoops, I didn't mean to pause that. So in terrestrial canopies like a field, this is called honami. In aquatic canopies like seagrass, this is called monami. I believe this term originated from a paper by Ray Grizzle, who's from here at UNH. So we can see there are clearly some periodic structures that are being shed from the wind blowing over this canopy. And we can see that this looks very similar to what you saw in that surface sloped field. So now we can get back to our original question, which was, how do interactions between aquatic ecosystems and the surrounding flow then manifest at the water surface? So to do this, I ran a set of 27 different experiments during my PhD with a wide range of canopy heights. So that's the variable HC that you can see here. A range of canopy densities, so how tightly packed these model vegetation stems are, and a range of flow speeds. So generally high Reynolds number, but a range. And then for that, we measured the free surface using that technique I had showed that's called a synthetic Schlieren technique. So we get the gradient in the free surface in space and time. And we also took some measurements of the velocity just downstream of the canopy, so we could understand this constant velocity within the canopy, UC, this sort of free stream velocity, US, and then understand the shear or the strength of the velocity profile, the steepness of the velocity profile right around the canopy height. So we wanted to see if we could compare these interior flow measurements with these surface measurements, and if there was some amount of connection or predictive ability that we could have. So I'll quickly go over the other variables. I introduced H minus HC in one of the other figures. So this is the gap between the top of the canopy and the water surface. So we have a constant water depth of capital H over all experiments. And here I'll be defining X in the streamwise direction and Z in the vertical direction. So just to show you how the mean velocity over depth changes with different canopy parameters, here are measurements from 3 different canopy heights, which are indicated by the horizontal dotted black lines that you see. And you can see that more of the flow is directed over the canopy when we have this kind of, it's basically a semi-porous obstruction in the flow. So we have greatly reduced velocities within the canopy and then faster velocities above it. And generally, we can model velocity profiles of this kind as a hyperbolic tangent. So these are the dashed blue lines that you see there. They're just fits to this equation. And so this equation, the hyperbolic tangent model for the mean velocity as a function of height is a function of delta U, which is the difference between that free stream and within canopy velocity. The height of the inflection point, which is about the same as the height of the canopy here, so where the concavity of the velocity profile changes. The thickness of the mixing layer, so kind of an expression of if you transition between your upper and lower velocity very quickly, theta will be smaller. If it takes a longer time or a longer distance, theta will be larger. And then U bar, which is just the depth average velocity, or essentially the mean of this within canopy and above canopy velocity. So these are 4 parameters that we can compare to quantities that we can get from the surface slope field. So let's go back to our animation really briefly. So you may remember I said that we see a characteristic shedding frequency in this surface slope signal. We see a characteristic kind of wavelength between peak to peak or trough to trough of these positive and negative values of surface slope. And we also see a kind of characteristic speed of these vortex structures as they're propagating downstream. So we can compute these quantities from the surface slope field and then compare it to the quantities of the mean interior velocity profile. So we can answer our, sort of get at our initial question, which was how do surface and interior measurements relate? So we can first look at the general flow structure. And just as a reminder, here's a little figure of what US and UC were, so the within canopy and the near surface or free stream velocity. So we can compare U bar, which was the average of these two, to the measured vortex speed at the water surface. We see there's a very strong correlation between those two. And we can also compare the vortex speed at the water surface to delta U, which was just the difference between these two velocities. And again, we see that there's a strong correlation. There's some scatter that can be explained by the canopy density. But in general, we see there's some very strong agreement between the vortex speed and then these parameters that you can't measure unless you put an instrument in the water when you're out in the field. And then we can also compare the vortex size with some of the geometry of the problem. So here I'm comparing the vortex size at the surface on the x-axis against basically H minus HC, so this gap between the top of the canopy and the free surface. We see there's, again, strong agreement. It kind of levels out when we get to I believe this was, so these are the very shortest canopies, which tend to, there's kind of a limit where you might not see a signal at the free surface. And then again, there's a correlation between the vortex size at the surface and theta, which was that mixing length, or the momentum thickness. And so this is great. We saw there are some correlations, but so what? I want to take this a step further and say, okay, can these surface measurements then be used as a predictive tool? So say if we went to a lab flume, or if we went to a seagrass bed in the real world, could we understand the flow structure and the geometry just by measuring the free surface without dipping our hands in the water, without having to put an instrument in the water or anything? So we have these relationships that I had shown on the previous slide, relating the measurements at the surface to the 4 variables in this equation for the shape of the mean velocity profile. So if we plug in these parameterizations that we found, we can get an equation for the mean velocity over depth that is solely a function of the local water depth, which is capital H, the length scale of the vortices, basically their wavelength, and the speed of the vortices at the surface. So these last 2 are things that you could measure purely from some remote sensing technique. The water depth, maybe you can stick a meter stick in the water. So this was a very nice collapse. And we can see that we can then plug this in, don't look at all of these figures individually, but we can see, so this is using this parameterization to try to reconstruct the velocity profiles. The red are these, reconstructions, this model, and the black circles are the experimental data that was measured. So here we're capturing variation due to flow speed, due to the height of the model vegetation, and the density of that model vegetation. And so this is, really exciting. You could, in theory, I could close my eyes. Someone could put some model canopy into a flume and run it at some arbitrary flow rate. And I could turn on these cameras and track perturbations and the free surface slope, and then tell you what the mean velocity profile over depth looked like. So this has implications in a few different areas. So first, we could think about remote sensing and field scale operations. And I'll talk about this in my last slides, where I'm talking about the directions to take this work. So for example, if you could measure the length scale of this vortex shedding, things like that, if we were able to characterize the dominant flow length scales, this has ecological implications. This can tell us maybe where or how far away are seeds or propagules of aquatic vegetation, how far away are these carried, how far is sediment transported, how far of a hydrodynamic effect does a seagrass bed have. And we were also able to measure a velocity of the vortices that are propagating over the canopy, which relates to some of these depth average velocities and within canopy velocities. And so this has implications for models of erosion or nutrient uptake. The nutrient uptake of seagrass blades has been shown to be proportional to the velocity that those blades are exposed to. So if you could remotely sense, the approximate velocity that a seagrass bed is being exposed to, you might be able to essentially remotely sense a driver of a biogeochemical cycle. So I might go to my conclusion slide for this. So just to summarize, we were motivated by this bathymetry inversion problem, where we wanted to know how interactions between aquatic ecosystems and the surrounding flow manifest at the water surface. And we found that free surface measurements allow us to essentially reconstruct the canopy-induced velocity profiles. And we saw that the surface signature is indicative of both the subsurface flow structure as well as the subsurface geometry. So that was our first case study. So let's go on to the next one, which is some work from my postdoc at the University of California, Merced, where we were looking at what fluid processes govern the subsurface retention of oil droplets. So our broader motivation for this work, here are a few examples. So one use of these things like bubbles and particles and droplets in a density stratified fluid. Bubble diffusers are often used in stratified lakes. So you have some bubble plumes that are trying to mix out this thermocline, the transition between different density of water. These are generally high Reynolds number flows, very energetic. At the much lower Reynolds number end, we have marine snow, which are small aggregates of organic matter, which have been shown that they tend to accumulate at thermoclines or pycnoclines in the ocean. And then at the sort of intermediate Reynolds number range, we have things like oil well leaks. So shown here are some images of oil and gas that were captured by a bubbleometer. It was basically this, I don't know how to describe it, this box that had you can kind of see some sloping funnel part at the top. So all of these oil droplets, and you can see a few gas bubbles in there too, would be kind of just rise into this chamber where they could image what the droplets look like. So a number of papers looking at these sort of dynamics, looking at bubbles or particles or droplets in a stratified fluid, have observed a very significant slowdown in an object's motion as it interacts with a pycnocline or a thermocline, again, that transition between two densities, and have attributed it to something called stratification drag, which is kind of a nebulous term. It's not necessarily a drag in the way that we think about drag. And so the nature of this sort of force has only recently been well characterized in some recent studies. So the question that we wanted to ask was, what are the dynamics that are governing the retention of a single droplet in stratification? So if we zoom in on this picture captured here in the bubbleometer, if we just look at the scale of a single oil droplet, what is happening? And we also wanted to be able to quantify the kind of time scale or the length of time that a droplet might be delayed from rising to the surface due to interactions with stratification. So let's look at a little cartoon of the kind of things that are happening at the scale of a single droplet. So here we have some lower layer fluid that is a higher density. This will be indicated by rho sub L. There's some finite transition between the two of some thickness H. And then we have an upper layer fluid that is a lower density. And then we have a droplet that's rising. It has some diameter D. In the lower layer, it will reach a terminal velocity UL, so the velocity in the lower layer. It will rise towards the surface. It will carry some denser fluid with it and drag it with it. But eventually the effects of that entrained fluid will be small enough that it can asymptote to an upper layer terminal velocity UU. So overall, the oil is less dense than both layers. So you would think a single oil droplet would just rise to the free surface, but in fact, we see a significant slowdown and a significant delay, which we have quantified. So the way that we looked at this experimentally was using a tank that has a little flange that you can disconnect from it, have different sort of needles for introducing oil at the bottom. And so then we took this tank and we would fill it with salt water in the lower layer for rho L, and then with fresh water in the upper layer. And we could control the thickness of the transition between the two. So here's a plot of density versus depth. And you can see marked in gray is what we'll call the transition region, the area where we have some density gradient as we're transitioning between salt and fresh water. And so we would then release an oil drop at the bottom of the tank and use a camera to track its position over height. And we would use a ruler that would calibrate and allow us to remove effects of the different indices of refraction when you have fresh and salt water. So an important parameter to note, if you haven't been exposed to it before, is the buoyancy frequency, which is indicated by the variable n, which is essentially the frequency if you displaced a parcel of fluid in the center of this kind of linearly stratified region. If you displaced a parcel of fluid up or down, it would then oscillate at some characteristic frequency that is a function of the gradient, basically the slope of this line. So we'll see that coming into play in some of the parameters that we can vary. So if we have a thicker layer, then d rho dz is smaller, and we have a smaller buoyancy frequency or a larger period of oscillation. So for these experiments, in addition to that, just position tracking data, we also ran a few experiments where we collected some flow visualization using the shadow graph technique. So for this, we have a light source, and then we have a lens that makes it so all of the light rays are coming in perfectly parallel to the tank. And then we would put some drafting paper on the other side where the shadow of the droplet and the shadow of its wake would be visualized, and then we have a camera looking at that. So basically, when you have a density gradient, that will focus or spread out the light rays that are coming in, and we're able to visualize how the droplet is distorting the density field. So we ran, I think, something like 180 different experiments, and we were able to then vary things like the Froude number, the Reynolds number, the relative density between the drop and the surrounding upper layer fluid, and then the relative layer thickness. So the thickness of that transition between the two densities, kind of this gradient here, the relative length of that to the diameter of the droplet. So we could explore a range of the parameter space. And so we can see one of these shadow graph videos in the next slide. So I will play this video. And I guess, again, it won't look quite as nice as it looks on my screen for your screens, maybe. But we can see in the bottom right here, this is the velocity of the droplet versus time. And it has this really significant slowdown where its velocity almost goes to 0. And this actually happens right near the top of this transition region. So this is where this line, if you can see it, is where we transition to just fresh water. We can compare this to another case that basically has the same buoyancy frequency and thickness of this transition region and droplet density, but is just a slightly smaller diameter of droplet. And we'll see some different wake structures. This one has a much more symmetric wake that is shed. We can actually see an internal wave field that's being generated here. You can kind of see some light and dark bands that are radiating off of it. And again, we see this very significant slowdown, kind of an overshoot, or I guess it's an undershoot of velocity. So we wanted to know, how does this slowdown relate to the environmental parameters or the parameters of our experiment? And I guess I'll just emphasize that these are just two cases, but we see this kind of significant slowdown, and the time it takes for the droplet to then recover to some constant velocity once it's in a homogeneous density. That's what we're interested in. So we quantified this. Time scale, the time it takes for the droplet to first pass its upper layer terminal velocity and to then recover to it. This is basically the duration of time over which there is some velocity deficit. So we can measure this for all of our different experiments and then non-dimensionalize it so that we have now this entrainment time scale, TE, times the buoyancy frequency. We want to non-dimensionalize so that we can look at the ratio of forces or the ratio of timescales, then our results will be applicable to other experiments or field phenomena that are a different scale, as long as these sort of ratios remain the same. So we could then compare this non-dimensional entrainment timescale, basically how long is a droplet significantly impacted by a change in density by this stratification. We can plot this against the Froude number, which is the ratio of the upper layer terminal velocity to the buoyancy frequency times diameter. And I'll kind of explain what this ratio means in the next slide, but we see that there's a strong trend of the entrainment timescale with the Froude number. So for very low Froude numbers, we have very long times over which the droplet's motion is affected by stratification. The very large Froude numbers, it's not really affected very strongly. So if we can kind of break this behavior into two different regimes. So if we look at for Froude number greater than 1, we can rearrange the Froude number, or we can rearrange this equation to then be looking at the ratio of the buoyancy timescale. So I guess the period at which some parcel of fluid would oscillate if it were displaced in a linear stratification. So Froude number greater than 1 means that the timescale of the buoyancy is greater than the timescale of the drop motion, or the inertial timescale. In that case, we see that the drop doesn't really experience any effects from the stratification. Whereas for a Froude number smaller than 1, in that case, our buoyancy timescale is less than the timescale of the droplet's motion, and the droplet kind of feels and interacts with and is significantly impacted by the ambient stratification. You could also think of the Froude number as a ratio of velocity scales. So some characteristic velocity scale of the droplet relative to maybe some characteristic internal wave velocity scale. So the droplet basically, for a very low Froude number, the droplet velocity is so low that it doesn't have the speed to really punch through this sharp stratification. So what does this mean in the context of the videos that I showed earlier? Let's see, we'll go back to these. I'll play the videos again. So here we had two droplets with really different and very striking and beautiful wake structures. And you might say, oh, maybe this large scale fluid flow is affecting the droplet's motion. This is what's causing this long time scale. But in fact, these two cases have very similar Froude numbers and have very significant times over which they are impacted by the stratification. So it seems like the far field wake dynamics, which vary greatly both within and below the transition region, don't actually impact the dynamics of retention. Some initial measurements seem to indicate that it's instead the very local wake, so this kind of trailing tail of fluid that the droplet is dragging with it. And if we measure the diameter of this wake over time, that's what's shown here. So the diameter of this wake relative to the droplet diameter versus non-dimensional time. And we see that in general, this wake is just decaying over time. These vertical lines that I'm showing represent the entrainment timescale for all of these different cases. And we see that the wake kind of decays to about 1/4 to a half of the droplet diameter in about this entrainment timescale length. So it seems like it might be, it's dragging this mass of denser fluid with it that's slowing it down once that mass, that local tail of fluid is small enough, it's not significantly impacting the droplet's motion. There are some other interesting forces. If any of my students from IAM, from ocean hydrodynamics are in the audience, there's another force that comes from baroclinic torque, the misalignment of density and pressure gradients that cause shear at the drop surface. We don't have vorticity measurements, so unfortunately we can't quantify those effects as well in this experiment. So just to summarize and wrap up this part, We saw that drop retention is governed by the Froude number, and for Froude number less than 1, the droplets were more significantly retained and interacted with the ambient stratification, and this was independent of the far field wake structures, with the caveat that for plume scale trapping, there's all this large scale turbulent entrainment of the ambient fluid and multi-droplet interactions that are also important. So I hope this will motivate one of the future work projects that I'll discuss. It looks like, I'm guessing I maybe have 5 minutes to talk about some future work, hopefully. You can shout at me if I don't. So I've got just 3 more slides to talk about the future directions of these sort of topics. So the first is looking at the surface signature of submerged vegetation. All of the experiments I showed to you today were using rigid wooden dowels as model vegetation. But we know that if you use flexible vegetation that is scaled to have the same flexibility or buoyancy as real seagrass, that changes the velocity profile to some degree. We still see this vortex shedding, but the vortices tend to be somewhat larger. So we want to know, how does the surface signature then vary with flexible versus rigid vegetation? Speaking of flexible vegetation, the question is, can we observe this sort of vortex shedding signature in the field? And is it distinguishable from other surface forcing, things like wind or waves? And then kind of the big question, the big picture goal here is, can we leverage this to remotely monitor eelgrass habitats in Great Bay? And with what remote sensing technology? And if there are any CCOM people or other people out there that know more about remote sensing in the field than I do, I would love to talk to you. And finally, I have a PhD student that he might be tuning in from Mauritius, which is still under some travel restrictions. But Vivek is an OE PhD student who just started this fall, who will likely be working on this problem. So if you see him in any of your classes or anything remotely, say hi. And another direction we're going into is looking at stereo imaging with more complex roughness than just these regular arrays of wooden dowels. So for example, I'm showing an image here that's from Vaid Chirayath, who's at NASA. He was an aeroastro student at Stanford. So he developed this technique called fluid lensing that basically uses the water surface as a kind of like magnifying glass to magnify different features when you have some curvature. And so he has been able to get really detailed measurements of coral reefs. I think this one is in American Samoa. So this is from a paper called Drones That See Through Waves. So he's basically kind of doing the opposite of what I've shown you. He's using waves to then just measure bathymetry and not caring so much about the wave field. But the question arises, can we use complex roughness features that I was able to track in the first part of this presentation? Can we use some sort of feature tracking algorithms to then serve as virtual wave gauges? And so we're in the very preliminary stages of this project right now, but Matthias Page is an undergrad researcher who's been working with me in developing a wave tank. So we're very excited to see if we can try to get some measurements like this, maybe 3D print some corals or something, and try to track some very distinct features on those through the water surface. And then finally, the other direction is looking at surfacing buoyant plumes. So looking at the surface signature of a plume, whether that's an oil plume or a freshwater plume or a bubble plume. Can we tell some information about the discharge rate or the turbulence that's created by that plume? So an example of this is meltwater discharge from a glacier, which would come out at the base of the glacier face and rises to the surface. A lot of the work that's looked at surfacing plumes has looked at a very mean time averaged sense. They don't really look at the instantaneous turbulent structures that are at the free surface. And so I think that's an important direction to go in. If you are more curious about just buoyant plumes in general, you should talk to Liz Widener, who is planning some experiments in the engineering tank. And it's been really fun working with her on that this spring and summer. And then I also talked about oil plumes, so we might want to know, is there some surface signature, any amount of upwelling at the surface? I don't know if a plume probably has decayed by then, but something that you could maybe imagine doing would be doing some laser sheet imaging of the plume itself, looking at the turbulent structures subsurface, and then looking at the turbulent structures that you might see at the free surface. And so I've been, I guess, working on some initial ideas about this with my, my former postdoc advisors at the University of California, Merced. This is an image that they took right when I was leaving. This is looking at a, I guess what's the word, a sphere that's being dragged upwards in a tank, and it has some outlet holes around the edge to pump some dye. And so they scan a laser sheet back and forth very fast. They have a very high-speed camera, and they can kind of see the wake structure of that sphere. So using techniques like this, using PIV, using some laser-induced fluorescence, things like that, the direction we're hoping to take this project in is looking at how does the surface signature of a turbulent plume then relate to the flow rate of that discharge of that plume, the intrusion of the plume if it's in a stratified environment, as well as turbulent entrainment of the ambient fluid. So can we remotely sense these things just by looking at the surface? And finally, if you see Zishan around Chase Ocean Engineering Lab, he just joined us after doing his master's at Oklahoma State, also looking at some turbulence things. So if you see him around Chase, say hi and say welcome to him as well. So I will, maybe I'll just put up my two big conclusions and say thank you to my collaborators that have worked on these projects with me, and open it up to questions.
Thanks, Tracy. Looks like we have a couple of questions here. The first is from Spencer, and he asked, how are the surface signatures affected by waves? Are the models depending on unidirectional flow? Yeah,
I think I missed a little bit. Are the models dependent on unidirectional flow? Yes, so the models are dependent, that velocity profile model is dependent on having unidirectional flow. I think there was a PhD student before me that had done some very preliminary measurements like this. And so they tried having some just monochromatic waves in the flume at about the same frequency as the shedding frequency. And they were able to kind of distinguish, if they looked at the spectra of the velocity field or the surface field, the vortex shedding has this kind of like wide-banded distinctive shape, whereas I guess the waves, because they were monochromatic, had a much more distinct peak. And so they could kind of distinguish that, but that is an open question.
And then the next question is from Liz. She goes, Tracy, great talk. Going back to your first topic, I was wondering what might be the effect of change in density of seagrass or other canopy cover on the flow patterns you're trying to measure. Do you think a dense versus thin patch of seagrass would alter the surface flow in a measurable way? And is this something that you've accounted for in this research?
Yes, so we did kind of account for it. We didn't explore a super wide range of densities. I'll try to find the slide. But I think, so there is some way that we couldn't quite account for the density. So in this upper right panel, the different colors of the points are the sparser density, the kind of intermediate density of the patch, and then a denser patch. And there's some scatter that, if we could somehow find the way that this would collapse the data better as a function of density, that might improve it. But I guess in terms of the general effect of the density of the seagrass on the flow patterns, it's basically just the effect is that as they're more tightly packed together, you get less through flow and more like overflow over the canopy. So then you end up with a sharper density gradient. and I guess slower velocities inside and faster velocities above.
Okay, and does anyone else have any questions? Feel free to enter the chat window in the Q&A. So I think that's all we have for questions. Thank you again, Tracy. This is great. And I think this is a great first seminar we have going. Next week, our speaker is from Raytheon. So we'll look forward to that next week. Thank you, everyone.